Today is November 15th, 2011. We're on lesson 5.3. Okay? Today we're going to be determining linear models. So a similar idea as of yesterday's, we were doing rate of change. This time we're applying them to linear models. I wanted you guys to get down the formulas and key concepts here. There are four major things that determine a linear model. We're going to go through examples of each of them. The very first one says that in a table of values, first differences are the same. So what that means, when we're talking about first differences, we're dealing with the dependent variable or the variable that would go on the y-axis. So I have a graph here of height and time. We're going to call time our x and height our y. So in other words, if time is our x, that means it's our dependent variable. Oh, sorry, other way around. X is our independent variable, and height is our dependent. Okay? So if we're finding first differences, we're going to be finding the first differences of the dependent variable, which is height, which would be on the y-axis. Now, in order to find first differences, we have to make sure that our x-axis goes up by the same amount, or it's increasing by the same amount. Luckily, it just goes up by 1, 2, 3, so that's consistent, so I can find first differences. So I'm going to be finding the difference between each of the numbers in our y-axis. So, first differences. I'm going to find the difference between 60 and 55. And we got 5. Then I'm going to take the difference between 55 and 40. 15. Then I'm going to take the difference between 40 and 15. It's 25. Okay? Each of these numbers, 5, 15, 25, they're changing. The first differences are changing. So, does that mean we have a linear model? No. Go ahead and read that. It says, in a table of values, first differences are the same. All of our first differences are different. That means this is not a linear model. Not linear. Okay? We're going to try that again with our hours and earnings. Again, our hours this time is going to be our x, and our earnings will be our y. So we have our independent variable and our dependent variable. We have to make sure that our independent variable is increasing by the same amount. So we quickly take a look. It's consistently going up by the number 5. So we're okay. I'm going to find the first differences of our earnings now. Now, I want to make a note. If you guys noticed, in our example 1a, we'll call it, I took the top number of the y and subtracted the next one below. So I went 60, 55. Then I decided to go 55, 40. And then finally 40, 15. That's fine. You can choose to take the top number and subtract the one beneath it. Or, like I'm going to show you in the next one, I'm going to take the one below and subtract the top number. As long as you're consistent with which order you put them in, you'll get a definitive answer. Okay? So in the next one, like I said, I'm going to start with the number below. 40 subtract 0, which is the opposite of what I did in 1a. 40 subtract 0 is 40. Then I'm going to take 80 subtract 40. As long as I keep that pattern of taking the number below and subtracting the one above, that's fine. It'll still work. 80 subtract 40, we get 40 again. 120 subtract 80, we get 40 again. So our first differences in this case are all of the exact same numbers, 40, 40, 40. So is this a linear model? Yes, this is a linear model. So anytime you have a table of values laid out like this and you have to determine if it's linear or nonlinear, you need to take the first differences of the numbers. Okay. Our next example is straightforward. You guys should have this knowledge already. But it is our second rule under our key concepts. The graph is a straight line. So if we have a graph of a straight line, we know we have a linear model. This one's going to take a couple seconds. Is this a linear model? Done. Next one. Is this a linear model?
No.
Not linear. Perfect. Just got to be able to see the two. Our second one was not a straight line. Our first one was. All right, our third example refers to our third rule. The equation of a linear model is y equals mx plus b. Okay? Now, what's important about this is our parent function y equals mx plus b. Is the major difference between a linear model and any other type of model will most likely be the exponent on our variable. So our variable here, y is equal to mx plus b. Does anyone know what m is going to stand for? Yes, good. M is our slope, and b is our... Good. So, m is our slope, b is our y-intercept, x is one of our major variables, and recall that x is to the power of 1. That'll be the easiest way to tell if something's a linear model. Also, you can always draw out the parent function right underneath, y equals mx plus b. In this case, what would be our slope for example 3a? 2. When you write slope out, so m is equal to 2, it's also equal to rise over run. And we're going to put that in our formulas. What would my rise be if my slope is 2? 2 over 1. And my run is 1. You would just turn it into a fraction. And a whole number is a fraction. You just put it over 1. What is our y-intercept? 5. Very good. Is this a linear model? Yes. This one is a linear model. I'll prove that one with the graph in a second. Our second one, let's write it again. Y equals mx plus b. Is our second model a linear model?
No.
Why not? Our x variable, there we go, is to the power of 2. So this is not linear. So if we take a look at our first one, we plugged in y equals 2x plus 5. When I plugged it into the calculator, we got a straight line, which also proves that we have a linear model. So we know that the first one was linear. We're going to test our second equation. The second equation was x squared plus 5. When we go to plug that in, so both of them are on here right now, we've got nonlinear. Does anyone know what this is by chance? Quadratic, good. Our second one represents a quadratic formula. Okay, so we know it is not linear. That was our main goal, just proving if it was linear or nonlinear. All right, example 4. This one is a word problem. It says a cup of coffee is reheated in a microwave. We have 2 different types of microwave. This one is a 500 watt microwave. This one is a 1000 watt microwave. Okay? And what these variables stand for, C is the temperature of the coffee in Celsius. That's why you use C. So temperature of coffee heated in a microwave. Temperature of coffee. S-I-U-S. and T is time in the microwave. Okay. Now, what I want you guys to do is kind of put all these things together and then make sense of what these equations are trying to tell us. So first off, we'll call the 500 watt microwave equation 1 and the 1000 watt microwave equation 2. What is our slope and what is our y-intercept? Just to start, for equation 1. What would our slope be in equation 1 and our y-intercept be? So 0.5 over 1, or what's another way I could write that? Good. 1 over 2. And our y-intercept is 20. So I've written them with a slope and y-intercept, and I also added rate of change here. Which of these discusses rate of change? Which of those two variables discuss rate of change? Sabra's told us that rate of change is how much something is essentially changing by, going up or down by that number. That means it's the slope. So whenever we talk about rate of change for a linear equation, we are talking about the slope. Okay, so we've circled it there. Our rate of change is the slope. So the rate of change here in time is 0.5, and what it's talking about is the degrees it changes in Celsius. What does the 20 stand for? We know it's the y-intercept, but in terms of making sense of this equation, what does 20 represent? 20 represent. So, again, Jennifer's told us that our 20 is representing our starting temperature. So, apparently, we put the coffees in these microwaves, both of them, at 20 degrees Celsius. Okay? That's for both of these. They both have the exact same y-intercept, 20 degrees Celsius. The rate of change is 1 over 2 for the 500 watt microwave and 1 over 1 for the 1000 watt microwave. So I'm going to quickly graph those for us. So we've quickly graphed these on it's essentially a graphing calculator. I have my two equations, 1 and 2. They both have the exact same y-intercept. We know that the coffee went in at 20 degrees Celsius. Which of these had a steeper slope? Equation 1 or equation 2? I know I didn't tell you which was which when I put these in. Clearly one has a steeper slope. 2. The slope of 2 is 1 over 1. So in other words, it's going over 1 block, up 1 block, over 1 block, up 1 block. That's its rate of change. Our other one is more horizontal. I wish I had different colors, but it goes a rise of 1 and over 2. A rise of 1 and over 2. So, let's get rid of all that. When you guys are looking at this, when we're comparing again equation 1 and equation 2, which of these heats the coffee faster? Equation 1 or equation 2? Equation 1. Remember, it has a steeper rate of change, so the temperature of the coffee is increasing. Our y-axis was our temperature in Celsius, and our x-axis was in time. Let's say it was seconds. So, according to this, if I wanted to get to 30 degrees Celsius, I would only need to put the coffee in the microwave for 10 seconds. If I was using the 1000 watt microwave, makes sense, 1000 watts, more heat to it. If I want to get to 30 degrees Celsius with the other microwave, I'd have to put it in for twice as long. I'd have to use 20 seconds. So the rate of change is not as steep in our second equation. All right, example 4, we have a scatter plot. Two different variables. We can really make up what they are. We'll say this is time and intelligence. Okay? And it's for a monkey. Just so none of you guys think it's for you. No, it isn't valid. Okay, what we need to do in this question, the question is asking us to determine a line of best fit. So in this question, like I was saying before, they want us to first set up a line of best fit. And then part B, this is the difficult part. They want you to determine the equation of the line. So, our line of best fit through this data is relatively straightforward. This looks like it would be a good line of best fit. Pretty simple for our A. We didn't really have any outliers to change our numbers. It all roughly falls around that line. Now, the difficult part is our line of best fit. Remember, the equation for a linear model is y is equal to mx plus b. M is our slope. B is our y-intercept. So, quickly looking at this, we got a bit lucky. What is our y-intercept? 4. That's a good number to use. Pretty straightforward. There's an easy one. So we have y equals mx. Since our b was the number 4, plus 4. Now our slope. We have to figure out what the slope of this equation is. So there are two ways we can do this. We have our one point, which is at 0 and 4. I have to find another coordinate on the line. I'm going to choose this number here, which is at 7 and 8. There are two ways we can find our slope. First off, this can be an xy value, which we can plug right into our equation, or we can use our rate of change formula, which is y2 minus y1 and x2 minus x1. So I'm going to show you two ways to solve for the slope. I think it is. So what I meant by the two of those, I'm going to split this down the middle. We have our equation, y equals mx plus 4. Our other point was at 7 and 8. So that will be our x and y value. I'm going to replace the x and the y in the equations with those two numbers and then isolate for slope, our m. The other way we could have done this is we have our two coordinates. One is at 0 and 4. The other, again, is at 7 and 8. And we can use our slope formula, which is y2, subtract y1, divided by x2, subtract x1. Both of these will work to find our slope. I'm going to call this coordinate 1 and coordinate 2. It's always best to label your coordinates. That way you don't get confused when you're plugging them in. This will be our x1, y1, x2, y2. So I'll do the one on the left first, then the one on the right next. We have our coordinates. Our y value was the number 8. So we replace y with 8. M. Our x is 7, so we replace x with 7 plus 4. Now we have to isolate m, so I want to move all the constants to the other side of the equation. So think of reverse BEDMAS. I'm going to be moving the positive, the plus 4 first. So I get 8, subtract 4, because the positive 4 becomes negative on the other side. And technically m times 7, anyone know what it is? 7m. Good. 8 subtract 4 is 4, is equal to 7m. To move that 7, I need to divide by 7 on both sides. So we end up with 7 over 4. Sorry, 4 over 7 equals m, or 4 divided by 7, 0.57 we'll call it. 0.57 as our slope. Okay. Now I'm going to show you on the second one, our y2 was 8. y1 was 4, so 8 subtract 4. Divided by x2 is 7. x1 is 0. Minus 7 is equal to m. On top, we're going to get 4. 8 subtract 4 is 4. 7 subtract 0 is 7. 4 over 7 is our m. It's the exact same thing, so again, or 0.57. Now here's the important part. We have to put into our equation. Remember, our b was 4, and our m is 4 over 7, or if you like the decimal, 0.57. Our equation of our line of best fit was y is equal to 4 over 7 x plus 4, or y equals 0.57x plus 4. And we're going to quickly prove that, just to make sure that that would be our graph. I know we did a lot there. So we have our equation. We plug it in. I'm going to have to move a little. There we go. Our y-intercept was number 4. And when we go up 4, 1, 2, 3, 4, we went over 7. And that makes sense. There's our, what is it, 8 and 7? Yeah. There's our point of 7, and 8, and 0 and 4. So that worked out perfect. We got the right line of best fit.